Okay, welcome everyone. So let's consider the following example that we've been discussing, and that is we want to determine whether a vector b, which is in R3, which has coordinates 6, -2, 10, whether that is in the span of a set of two vectors. V1 is 1, 0, -2, V2 is 0, 1, -1. And so let's frame this question in a couple of different ways. And so by definition, what this is asking is this vector 6, -2, -10, can it be written as some linear combination of vector v1 and vector v2? And on the previous videos, we looked at how we can restate this using a matrix equation. Namely, we create a matrix of column vectors for each vector in the spanning set. We have a vector of our weights, and then we want to see whether it's possible to find weights x1 and x2 so that we wind up with vector b on the right side. Prior to learning about matrix vector operations, multiplications, we expressed this same question as a system of linear equations. In this case, we have a system of three linear equations with two unknowns, the two weights x1 and x2. So this question about is b in the span of two vectors, by definition, we've got this equation, and we can represent this vector equation either as a system of linear equations, or we can represent it as a matrix equation. And so to generalize this problem of saying, okay, is this vector b in the spanning set of these two vectors, that's equivalent to asking, does this matrix equation ax equal b have a solution? And so solving this matrix equation is equivalent to solving this question, which is, okay, can we find linear combinations of these vectors that are going to give us b, which is equivalent to a system of linear equations such as the one below that are going to have augmented matrix a1, a2, b. So we can solve this matrix equation using methods that we've already discussed, namely working with augmented matrices and using a row reduction on those. Okay, so on the previous slide, we set up three different ways of expressing the same equation. Namely, we have a matrix equation, matrix A times vector x is equal to some other vector b. And this comes, one way that we can see equations like this arise are asking questions like, is b, vector b, in the spanning set of vectors a1, a2, up to an? So this matrix equation we showed can be written as this vector equation over here, and this vector equation has is a system of linear equations which has the following augmented matrix. And so a very natural first question to ask would be, well, how can we determine whether a matrix equation has a solution at all? And we can fall back on what we already discussed with linear systems. And so namely, this equation, this matrix equation, ax equals b, is going to have a solution if and only if b is a linear combination of the columns of matrix A, since it's equivalent to this question over here. So if b can be written as a linear combination of the column vectors of A, then this matrix equation is going to have a solution. So far we've mainly been asking questions such as above, like given a certain vector and a certain set of, and a spanning set of vectors, is this specific vector in the spanning set of vectors v1 up to vp? A more abstract question would be to ask, okay, can we generate all vectors, in this case, all vectors in R3 from a set of spanning vectors? So rather than pick a specific vector b, what we want to know is, given any vector b in R3, and we'll leave the coordinates for b as arbitrary, b1, b2, and b3, can that be written as a linear combination of these three vectors that I'll call a1, a2, and a3? And as we discussed just prior to this, this question is identical to saying, can we solve some linear system of equations with the corresponding augmented matrix? where in this matrix, the first column is A1, the second column is vector A2, the third column is A3, and we have a fourth column, which is now going to just include this arbitrary vector B. And so in particular, in this case, right here is our augmented matrix. A1 was 1, 1, minus 3, so that's our first column. A2 is 1, 0, minus 3, that's column 2. Column 3 is A3, which is 6, 8, 6. And then we have the fourth column is this column of B1, B2, and B3 for arbitrary matrix B. And then we can do row operations, elementary row operations to express this in row echelon form, reduced row echelon form, and then look for solutions. So I will kind of go through that part rather quickly here since we've been working with these in previous sections, but I can replace row 2 with minus 1 times row 1 plus row 2, and that gives me a 0 beneath the first pivot in the first pivot column. And there are the other corresponding entries. So over here, I'm just going to leave this as B2 minus B1. And then we can get rid of the minus 3 down here below the pivot by multiplying row 1 by 3 and adding it to row 3. And that results in the following matrix. So now we get a 0 here, we get a 0 over here, we have 24, and then we have B3 plus 3B1. And so at this point, we have the matrix in row echelon form. It's not in reduced row echelon form. But if we're just asking, do we have a solution? Is it possible to solve this system of equations that we started with up here? I can see at this point that yes, we definitely can solve this system because we have a pivot in every column corresponding to variable x1, x2, and x3. So in other words, no matter the values for B1, B2, and B3, which are this last column over here, no matter what these are, we can see that x1, x2, and x3 are all basic variables because they correspond to a pivot column. So this system is consistent. And so from the previous theorem, since this is a consistent system, we can solve this linear system of equations. That implies that, yes, we can get any vector B in R3 by taking linear combinations of vector A1, A2, and A3. So we've been framing this question, is a certain vector in the spanning set of a set of other vectors in several different ways by thinking about linear combinations of the vectors, which led us to linear systems of equations. And now we can express this using a matrix vector equation as well. So I want to summarize the connection between all of these on the next slide. So if we have a matrix A, which has m rows and n columns, then we've been working with different ways of framing the same sort of question. So on the one hand, we can take a look at the matrix equation, AX equals B. So for a given B, if we want to know whether or not this matrix equation has a solution, well, that is equivalent to asking, is this vector B in the spanning set of the columns of A? In other words, can B be written as a linear combination of the column vectors of A? Because really, this is how we led to matrix equation. So these two questions are exactly identical. And this is equivalent to saying, okay, do the columns of A span all of Rm? And this is equivalent to taking a look at the matrix A and putting it into kind of row echelon form and then looking at, does A have a pivot position in every row? And we actually don't even worry about B in this case, because remember on the previous slide, we were just really working with the first three columns of that augmented matrix. So these four statements are all equivalent, meaning if any one of them is true, then all of them are true, or if any one of them is false, then we know that all of them would be false.